Likewise, I might have other 4K pages that have same content. Same. And again, duplicate. So I'm using up a lot of memory to store the same information multiple times. So one of the technologies is like a page sharing technology. And what it does is it goes through the physical RAM. And for each page of memory, it creates a hash value. So something that should be mathematically unique, but at a very small value based on the content. So over a period of time, it goes through the physical RAM, depending on how much. This could take minutes, hours. And it says, well, hey, look, the hash value of this page, and that one, it's all the same. So it does a bit-by-bit comparison. And if it finds they really are the same content, well, I don't need to store it 5 times. It stores it once. And all of these pages effectively link to that single copy of the page. And they all reference it. Same for these guys. Well, they're all the same. I just store it once. So you can see there's good memory savings there. Like I say, it takes time to do this, but you're going to see those memory savings. Again, one of the troubles we're now seeing with this sort of page sharing technology is this works fantastic on a 4K page. The chances of finding 4K pages that are exactly the same are pretty good. The shift now is towards large memory pages. So we have a 2 megabyte memory page. Well, the chances of finding identical content over a 2 megabyte memory page is much smaller than trying to find duplicate on a 4K memory page. So essentially what that means is the chances of really saving memory by finding duplicate 2 meg pages over the same OS instance or different OS instances is really being negated. And that is the shift. And again, it's not just a Microsoft shift, Linux, and some of the new processors. I'm saying 2 megabytes. They're talking in the future, some of the newer processors that are going to come out are supporting gigabyte size pages. So this is only going to get a bigger issue. So the transparent page sharing, by looking at memory pages that have exactly the same content, yeah, under the older operating systems that didn't use large memory pages, you get some savings. And that can be significant, especially if I've got lots and lots of copies of the same OS with the same stuff running. But we move to large memory pages, you see a much smaller amount of saving. And there's other factors. We have something called address space load randomization. And essentially what that does is, instead of the kernel loading its key pieces of code into the same part of memory every time it boots up, which leaves it maybe vulnerable to malware that knows to attack that page of memory, it now loads it in one of a random number of locations. So again, the memory is kind of scattered around differently, but that's not the primary factor. The big thing is this large memory adoption. Now, technical bit, you may say, well, why do I care about large memory pages? Well, you think back to the old days of floppy disks, where I can only get so much information on a floppy disk. Well, that's like having a small memory page. So to store my large amount of data, I have to use lots and lots of pages. When I move to large memory pages, I get a lot more data in each page of memory. Now, remember the way memory really works. I need a new ball eraser, obviously, or new pens. An application doesn't see the physical RAM. The application sees its virtual address space. And then underneath here we have the physical RAM. So the application sees a nice contiguous memory space, which in reality is scattered all over the physical RAM. And we have a page table. And the page table is basically responsible for saying, well, that page in the virtual address space actually sits here in the physical RAM. So when it tries to access memory, it says this page and this offset, and it has to go to the page table and say, where does that memory really exist? And that's called walking the page table. Well, that's fairly slow. So it's something called a translation look-aside buffer, TLB, and that has a finite number of entries in it. And it stores the content of those page tables for the most recently used lookups. So it's very, very fast. It finds things almost instantly. Well, I only have a finite number of entries, let's say 128. So if I'm using small memory pages, this TLB, well, it's only going to address a very small portion of my physical RAM, which means I'm going to have to do walking the page table a lot. if I'm using large memory pages, that same size look-aside buffer is going to be able to access and address a lot more of the physical RAM. I mean, if you go from 4K to 2 meg, that's 512 times more memory is addressable. So it means I'm doing the page table walk a lot less. I'm finding my data a lot more quickly. So we want the large memory pages. It's good for us, it's good for the performance. So that's something we really want to adopt, and that's why we've got this shift in Windows to large memory pages. So that's page sharing. So again, it's a neat idea, but just as the industry adopts these large pages, it's becoming less and less of a major factor. I mean, you've probably heard of, let's say, disk paging. And that's something no one really wants to do. It's usually like a last-ditch attempt. And the idea here is that the virtual machine has their virtual memory, and let's say the hypervisor has overcommitted memory so much that it can't physically put the memory of the VM, certain pages, it just doesn't fit in the physical RAM anymore. So what it does is it has basically a page table, and it randomly selects certain pages from the virtual machine and just dumps them out to disk instead of writing its physical RAM. Now obviously disk is multitude times slower than RAM, so we don't want this paging to occur, because this could be the kernel. I mean, it doesn't know anything about the guest operating system. It's saying you, and dumping it out to disk and hoping it's not something really critical. Now it can try and look at usage patterns, etc., but at the end of the day it could be paging out something that shouldn't be paged out. Now you may say, well wait, that doesn't make any sense. Operating systems page out to disk all the time. We have a page file in Windows. Yes, but if you think about what a page file in the operating system does, it's not randomly picking pages. This guest could have its own page file out to disk, but it's the OS within this virtual machine that's making that decision. So the OS knows, well, what's in each of these memory pages, and it can intelligently say, okay, this piece of memory I'm going to dump out to my page file, based on its knowledge of which process is using it, is it part of the kernel, how important it is. It's not randomly just picking memory from its own memory and chucking it out to disk. It's saying, okay, well obviously this is a kernel, I don't want to page that out ever, that's vitally important. These pages are used by this application that's not used it for a while, I can dump that safely out. So we don't mind paging within the guest operating system. It's intelligent, it can make the right decisions and dump out the least important memory. What we don't want is the hypervisor, which has no intelligence into how the memory is being used in the guest, and dumping it out. So we don't want to do that. So disk paging is generally a bad thing. So they're the sort of three main technologies you see in the industry. So what did we do with dynamic memory, with HyperV? Well, we didn't really do any of them. What we've actually done is we're now actually giving a virtual machine an initial amount of memory and a maximum amount of memory. And we've also set some other counters which I'll go into in a little bit. But essentially when the VM starts, let's say we configure a minimum of let's say 512 and a max of 2 gigabytes. When the VM turns on, it gets 512. And all 512 of that maps to physical RAM. So I'm using 512 of physical RAM. And I might have another virtual machine over here that also starts off with 500.